So using that same principle, if we have a child on a spinning merry-go-round, initially he's halfway between the center and the edge of the merry-go-round. As he walks to the middle, what effect does this have on angular momentum? Well, what changes angular momentum? A net external torque on the system. So I guess to answer this question, I would have to be a little more clear. What effect does this have on angular momentum? Well, angular momentum of what? Let's say for all these questions, let's say we're considering the child merry-go-round system. Is that a net external torque on the child/merry-go-round system? No. So angular momentum does not change. What about angular velocity? Well, he walks to the middle. So what does that mean? Now more mass is closer to the axis of rotation. So angular velocity increases as moving to the middle decreases moment of inertia while conserving angular momentum. And L equals I omega, so if you decrease I, omega goes up. You walk to the edge. What effect does that have on angular momentum? None. Angular momentum is the same, just like as in the previous problem. Angular velocity is the opposite of A. Angular velocity decreases as moving farther out increases the moment of inertia because now the mass is farther from the axis of rotation while the angular momentum is conserved. Now if we run to halfway between the center and the edge, and then the child begins running around the center in a circle. So initially, he's moving halfway between the edge and he's just going around with the merry-go-round. But then he starts running. So he's either, he's giving himself a velocity then relative to the merry-go-round. Okay. So what effect does that have? Well, the angular momentum for the system is conserved. So angular momentum is transferred between him and the merry-go-round. So if he runs in the direction the merry-go-round is already traveling, that is, if the merry-go-round is going counterclockwise and then he starts running counterclockwise relative to the merry-go-round, he gains angular momentum in that direction. So the merry-go-round loses angular momentum in that direction. So his omega increases, merry-go-round's angular velocity will decrease. And vice versa. If he starts running the opposite direction, he will lose angular momentum in the direction that he and the merry-go-round were going, and the merry-go-round will then gain that same amount of angular momentum. So I'll say and vice versa. If you're on a stationary merry-go-round, you started running around this way, and the merry-go-round would start spinning the opposite direction with equal angular momentum. Here's a classic problem that the AP exam likes. Got a uniform rod of mass L, or length L and mass 4m at rest in a flat frictionless table fixed to rotate around one end. So we've got a rod chilling out on a table, and it's anchored right there. Maybe it's nailed to the table or something, I don't know. And then a ball of mass m is moving with speed v, and it hits the end of the rod, bang. And in this case, it rebounds with speed v over 10. Now, if you consider the ball rod system, what is the net external torque on the system? Well, it's going to be 0, because the ball and rod are only exerting forces on each other. So while they each will change their angular momentum, there is no net torque on the system, so they will not change the system's total angular momentum. Now it's interesting to note that linear momentum is not conserved in this collision, because there is this axis that the rod is fixed around, and that will, when the rod would tend to start moving to the right, this axis will exert a force that will cause linear momentum to not be conserved. But it doesn't exert a torque, because that force is acting at the axis of rotation. You can also do this problem with the rod not anchored anywhere, and then conserve both angular and linear momentum. Anyway, so what is the angular speed of the rod? Well, we know that angular momentum is conserved, so L naught equals L final. And these types of problems are going to look a lot like collisions that we did when we were linear collisions. These are angular collisions where angular momentum is conserved, so we write initial angular momentum equals final angular momentum. Now we know the angular momentum of a point particle is just mvr. L is I omega. We talked about this for a point particle, but just a reminder, L is I omega for a point particle. I is mr squared, and omega is v over r. So mvr is the angular momentum, and we can use r being the distance of closest approach to that point. So that where does its distance of closest approach? Well, it's right here at the end of the rod. So initial angular momentum is mvr, and in this case r is the length of the rod, therefore L. Well, that's confusing, isn't it? We've got length L and L is angular momentum. Whoa. That's not great, but such is life. All right. The ball rebounds with speed v over 10. So initially, this ball's angular momentum, if you take the cross product of the radius vector with the velocity vector, you can see the angular momentum is upward. It's kind of like it's going in a circle this way around the axis of rotation. When it rebounds the other way, now it has angular momentum in the opposite direction. So that's again mvr, but it's in the opposite direction. Plus then whatever angular momentum the rod gains. Well, a rod with axis through the end, the moment of inertia of that is 1/3 ml squared. And then that angular velocity of the rod is what we're trying to find. So then we can calculate, I used a capital M. Gosh, I should really read my problems. The mass of the rod we're given is 4m. So we plug in 4m for the mass of the rod. The m cancels out. The factor of L cancels out. Move this over, so we've got 1v plus 1 over 10v. That's 11v over 10 is equal to 4/3 L omega final. So then the angular velocity of that rod is equal to, wow, that's kind of nasty, 33 v over 40 L. Whew. How much energy is lost in the collision? Well, how much energy is lost? That's kinetic energy. The change in kinetic energy is how much energy is lost. Our initial kinetic energy is all linear. It's just linear, 1/2 mv squared. Our final is 1/2 mv squared for the ball plus 1/2 I omega squared for the rod. And the rod has mass 4m. I is 1/3 m times L squared times omega squared. Whew. It's kind of nasty. L's go bye-bye. But there's this factor of 4/3 that was part of this. So that cancels out to 11 over 10 times 1/2 gives us 11 over 20 mv squared plus, ouch, 1 over 200 and I'm going to resort to my calculator here to take 1/2 minus 1 over 200 minus 11 over 20. So that gives us minus 11 over 200 mv squared. That's not good. Did I make a mistake? Okay, now I knew that looked weird because if I got a negative here, that means final energy was bigger than initial energy, and that's not good. That's not a good sign. I see what I did. I canceled 4/3 with 33 over 40, but I didn't square the 33 over 40. So you take 33 over 40 squared times 0.5 times 1 times 4/3. So it's not 11 over 20. It's this big nasty thing. 363 over 800, but that's actually less than 11 over 20. So now we add 1 over 200 and then take 1/2 minus that. There we go. And it turns out that our change in kinetic energy is we've lost 33 over 800 mv squared. That's how much kinetic energy we've lost. Pay attention to signs. They will alert you to errors.